So I'll be talking about the Goldman bracket, how it characterizes homeomorphisms. This is some of my own work, which was published in Comte in December 2011. This was actually a talk at our department's in-house symposium, so a lot of the emphasis was on questions related to the Goldman bracket. Yes, it's a simple result that I'll be talking about. So firstly, what is the question I'm concerned with? It's the general problem of topological rigidity. So maps between x and y are homotopic if phi can be composed continuously deformed to C. Basic idea of algebraic topology is you start treating maps that are homotopic as equal, and then when are spaces the same? Their spaces are same if they're homotopy equivalent. So there are maps from one to the other and the other to the first, from x to y and y to x. So compositions need not be equal to the identity, but instead are homotopic to the identity. Now homotopy equivalence is very, very far from homeomorphism, but here's the question. So given a homotopy equivalence, is a given homotopy equivalence homotopic to a homeomorphism? So the refinement of the question of whether homotopy equivalent spaces are homeomorphic, but it's a more useful formulation. So here's the comment. Euclidean spaces are all homotopy equivalent but are not homeomorphic if n is not m. So you expect to have some restrictions on x and y. For instance, they should both be of the same dimension, and ideally they should be manifolds for this to make sense. But suppose they are manifolds of the same dimension. One of the classical results is that if you have surfaces of the same dimension, then any homotopy equivalence between compact surfaces without boundary is homotopic to homeomorphism. I should emphasize without boundary. For closed surfaces, we do have topological rigidity. And so in higher dimensions, this is a rich kind of question. But we'll just concentrate on the two-dimensional case. So here, if you look at the three-holed sphere, that is, you take a sphere, remove the interiors of three disks on it, or you take a torus and remove the interior of a disk on it. Both of these are homotopy equivalent to a wedge of two spheres, as you will see in this picture, but they are not homeomorphic to each other, but even the number of boundary components is different. Okay. So the result I'll talk about is a characterization in the case of compact surfaces. I should emphasize a characterization. There are plenty of them, and the one that I give is simply a reformulation of a well-known characterization of Nielsen. And in fact, the proof is rather simple. I mean, it's simply a matter of just putting things together. And however, the statement I think is very attractive, which is the reason why I proved this theorem. So homotopy equivalence between compact oriented surfaces with boundaries homotopic to an orientation preserving homeomorphism if and only if it preserves the Goldman bracket. I haven't told you what the Goldman bracket is. That is what I'm advertising here. But it's a nice algebraic structure, and the statement is ideal. It says that if you look at a homotopy equivalence, it preserves this algebraic structure exactly when it's a homeomorphism. So it completely connects it. So besides the sort of attractiveness of this, a very nice algebraic structure giving a complete characterization, you have other reasons why things are nice. Goldman bracket is connected to string topology. In fact, string topology generalizes the Goldman bracket, hence the Floer homology on the tangent space. So at least this is a source of conjectures in other cases. So as I said, that talk, one of the goals was to raise a lot of questions. What happens in the case of open surfaces, that is surfaces which are not compact but with no boundary? The statement makes perfect sense. The proof doesn't work directly. It may not be difficult to make it work, but it directly doesn't work. Okay, so what is this Goldman bracket? So let's take two smooth closed curves. Here's the red curve and a blue curve and suppose they intersect only transversally in ordinary double points. So they intersect nicely. Then, as is well known, we can associate a sign to each intersection point. One of these signs will be positive, one of them will be negative. Okay. And the other thing we can do is we can resolve each intersection point to get a closed curve. So you cut and paste to get a closed curve at each intersection point. So that means that associated to each intersection point you have a number and you have a new closed curve. Okay. And what happens with what is the Goldman bracket? Informally, you take the formal sum of these closed curves with a given sign. Here's a little more of a formal description. For a surface sigma, you take, let C of sigma be the set of homotopy classes of curves on sigma, and the Langle alpha wrangle, this bracket denotes the equivalence class of the closed curve alpha. Okay. So suppose we take two closed curves, alpha and beta, smooth closed curves, which intersect nicely, transversally in double points. Okay. If P is in A intersection B, then alpha and beta can be viewed as loops beginning and ending at P. So the point P is in both alpha and beta. They are closed curves. You can base them at any point on them. So then we can multiply them as we do in the fundamental group. So that simply means we take the loop alpha followed by the loop beta. Okay. Start at P, go along alpha, come back to P, go along beta. This will give you a closed curve. Now we ignore the base point. We can also associate a sign. And so the Goldman bracket is this sum. The sum of the curves alpha and beta so far is the sum over all intersection points of epsilon p is the sign times the homotopy class of alpha star p beta. Well, Goldman proved many things about this. So here are three remarkable theorems which lay the foundation here. First one tells you that you can define the Goldman bracket not just on curves but actually on homotopy classes of curves. So if alpha is homotopic to alpha prime and beta is homotopic to beta prime, here we have two curves beta and beta prime which are homotopic, two blue curves, then the Goldman bracket of alpha beta is the Goldman bracket of alpha prime beta prime. Remember, in the target we are only looking at homotopy classes of curves. You see, now if you look at alpha and beta here, they intersect in 2 points. So the Goldman bracket gives you two terms, while beta, alpha and beta prime don't intersect at all. So Goldman bracket is 0. So the Goldman bracket of alpha and beta should also be 0 according to this. Okay, because alpha beta is this. Indeed, the two terms you get cancel. They cancel because in between alpha and beta there is a region which we'd call a bygone. So this is the on the other hand, in fact, from a modern viewpoint of this theorem is not particularly surprising, and there are many other structures which have this property too, because we know homotopy curves are related by cancelling bygones of this form. So and also monogons, and so one just has to see the change under this. So this is the first statement which gets us started. It tells you that you get a well-defined bilinear functional from the free abelian group on closed curves times itself to itself, I mean on this. So you have a bracket, or product, whatever you like to call it. Well, the second remarkable theorem is that this is a bracket. It's a Lie bracket. We have a functional from one abelian group cross another, cross itself to itself. It takes two elements in an abelian group and gives one. It satisfies the skew symmetry property as well as the Jacobi identity, which is the skew symmetric form in some sense of associativity. It's a very important and natural property. So the Goldman bracket remarkably satisfies these two properties. So a couple of questions. Is this group is this ring, not even a ring, it's a set, finitely generated as a Lie algebra? Possibly after replacing Z by R. Now, I should say, first of all, as a group, it's clearly not, because C of sigma is finite. But is it finitely generated as a Lie algebra? I'm inclined to think no, but it would be very interesting to prove it one way or the other. And the techniques involved in proving it would be interesting anyway. And this is, of course, over Z. That will also involve arithmetic issues. Let's just take R, which will involve only the geometric issues. Still, so far as I know, this question is not answered. It's a simpler question, and here I think the answer should be relatively clearly yes, and should not be so difficult. So you look at the sub-algebra, subgroup generated by simple curves. It's not a sub-algebra, otherwise it wouldn't make sense. So you took curves in C of sigma that are simple and look at formal linear combinations of them. Is the Lie algebra generated by this all of the Goldman algebra? This I would think is yes. And the most remarkable theorem of Goldman, which I'll be using here and which also gives this bracket its well-deserved fame, So suppose alpha is a simple closed curve and beta is any closed curve. Then their Goldman bracket is 0 if and only if beta can be homotopy to beta prime such that alpha intersection beta prime is empty. Okay, so to understand the statement, let's look at the easy half of this. Suppose alpha intersection beta is empty, they have no intersection point, so we have an empty sum, so the Goldman bracket is 0. Further, because if alpha intersection beta prime is 0, is empty, then because alpha and beta are is the same as the Goldman bracket is the same as alpha beta prime by what I said, it's trivial. Now the highly non-trivial point is the converse is true. That is, if you have the Goldman bracket 0, which may involve all sorts of cancellations, the result is still then it turns out that there were no real cancellations other than these bygones. That is, you could push alpha away from beta. Well, so here's another question. What is the kernel of the Goldman bracket? Okay, this is a statement which is closely related to the above result in the sense that if you are thinking of simple elements, I mean elements that are actually in C of sigma rather than formal linear combinations, that's answered immediately by the above question and in the general case by what we'll be using. Okay, so if sigma is a closed surface, then a curve is in the kernel. A single closed curve is in the kernel if and only if it's homotopically trivial. But what about a linear combination of curves? That's a question. So now we'll start our proof, which as I said is simply reformulating Nielsen's work. So let's take a compact surface, possibly with boundary. All this works even without boundary. So closed curve is peripheral if it's homotopic to a curve in the boundary. Okay. By using Goldman's third theorem and some well-known geometric topology, a closed curve is peripheral if and only if its Goldman bracket is 0 for all a closed curve alpha is peripheral if and only if its Goldman bracket with all closed curves beta is trivial. Okay, this will follow because if a curve is not peripheral, you can find a simple curve beta which intersects alpha in more than one point, which cannot be homotopy to be disjoint from alpha, and then apply Goldman's theorem for this. This is very useful because, as I said, of Nielsen's theorem, it says the homotopy equivalence between compact surfaces is homotopic to a homeomorphism if and only if it preserves peripheral curves. Whenever alpha is in sigma 1 is peripheral, so is its image. Okay, so we have most of our ingredients here. So here's the proof of the main theorem. It's a simple reformulation. Suppose we take a homotopy equivalence, okay, such that the Goldman bracket is preserved. Okay, the other side is trivial. So suppose, so by the above lemma, if you have a peripheral curve, so is its image. Okay, so you have a nice, it's easy to see. Oh, I didn't comment on this, but Goldman bracket, homotopy equivalence induces a bijection between homotopy classes of curves. So this map F star is already a bijection, so it's a Lie algebra isomorphism. So any characterization in terms of the Lie algebra works. Plus, of course, simple closed curve. I mean, closed curves go to closed curves, not linear combinations of closed curves. So by the above lemma, if alpha is contained in sigma, if a curve is peripheral, so is its image. Follows by Nielsen's theorem that F is homotopic to homeomorphism. Little work will tell you that it's actually orientation preserving. The converse is easy. Namely, if we have a homeomorphism, it preserves the Goldman bracket. Any reasonable topological structure is preserved. So this concludes the proof. Let me conclude this little screencast with a question. So is every Lie algebra isomorphism induced by homeomorphism? So what we have seen is Lie algebra isomorphisms induced by homotopy equivalences are in fact induced by homeomorphisms, and this gives a very elegant characterization of homeomorphisms. But what if we just had an abstract Lie algebra isomorphism? Then must it be induced by homeomorphism? I don't know. With this, I'll stop.